Hi, George Diamond here. Now today we're going to see if we can do a little calculus. All right? We're going to look at, specifically we're going to look at some optimization problems. I'm going to solve just a couple of problems. So I'm going to try to do about 4 today. Now, optimization problems are applied minimum maximum problems. These are some reading problems. All right? Now, in our textbook, this is section 3.7. All right? So we're going to see if we can do a couple of fairly common problems. But to get me started, I want to see if I can move my graduated cylinder out of the way here. So we'll move that. And let's go ahead and take a look at our first problem. Now, in just a minute, I'm going to take this down. So if you are copying the problem down, you need to go ahead and get it down. So I'm going to have to take this off to give me a little bit of extra room here. But so these are applied minimum maximum problems. So get started. Let's take a look at this first problem. So we're going to design an open box having a square base with a surface area of 108 square inches. Okay, what dimensions will produce a box with the maximum volume? So what will be the dimensions of a box with a maximum volume? And once again, it's an open box, so open at the top. Okay, having a square base with a surface area of 108 square inches. So to get it started, always start off. Now the first step in any type of applied problem like this, a reading problem, if you don't have a diagram already, you want to start off with a diagram. So it kind of gives you an idea of exactly what you're looking at. So let's do a little sketch here first. Erase this. This little sketch. So we're talking about a box. It will look like a rectangular solid, all right? So you're talking about has a square base. So like so. Open at the top. Okay. Now with our box, if you will, let's let the base is going to be a square, so let the base be x and x. All right, so it has a square base, right, so the base is a square, and let's let h represent the height. Right, so we'll do h for height. Okay. Now now start off. Let's recognize exactly what it is we're minimizing or maximizing here. And in this case, where it says what dimensions will produce a box with maximum volume. Right, so we're talking about the volume, so maximum volume with this problem here. So maximum volume. Now, when you look at a box, now a box is a rectangular solid. And remember, the volume of a rectangular solid is length times its width times its height. So you remember that from geometry. So in our case here, we're going to list our volume here as length times width will be x squared times our height. So this is going to be our volume problem that we're going to use. Now, just a minute, we'll have to take the derivative of this. But when you look at the volume problem, when you got our volume formula here, V equals x squared times h. Okay, it's written in terms of the volume is expressed in terms of x and h, which makes this a much harder problem when you have more than you've got three different variables, v, x, and h. So with this type of problem, we're going to see if we can remove either x or h. So we'll see if we can remove or eliminate one of our variables. Now, if you notice in this problem now, so that they give us a constraint. So you can't just make a box that's this infinitely big, right? So it has a square base with a surface area of 108 cubic inches. Right, so describe the surface area. So it has to have a surface area of 108 square inches, all right? So you can't make a box that's infinitely big. So with this particular problem now, to remove one of these variables, now this here is called our primary equation. Okay, this is our primary equation. Okay, this one we're going to work with. This is the one that has to be maximized, all right? So this is called our primary equation. Now, to eliminate one of our variables now, we're going to use a secondary equation. Okay, that's why they give us the 108 square inches. Now, that's a constraint. So we call this a secondary equation, or we're going to set up what's called a constraint equation. Right? So we need a secondary equation here. So a secondary equation. Now, the secondary equation is going to describe the surface area of this box. Now, the volume of the box is simply x squared times h. Let's see if we can describe the surface area. They tell us the surface area is 108 inches cubed, and we're going to use that constraint, this 108 inches squared. We're going to use 108 inches squared. We're going to use that fact to eliminate one of our variables from our volume formula and make it much easier to take the derivative of. So let's see if we can describe the surface area of our box. Now, surface area of this box, you're going to have to find the surface area. We're going to find the area. Now, it's open at the top, so you've got the four sides and you've got the base. So we're going to find the area of the base. So the area of the base, okay, plus the area of the sides. Now, you've got four sides here, so this will be 4 times the area of the sides of one side, if you will. All right, so to describe the surface area of our box, this is how we're going to describe the area of our box. So now the base is simply, area of the base is simply x times x. And we said the surface area is 108. So our secondary formula here, we're going to substitute 108 in for a. The area of the base would be x squared, okay, plus 4 times the area of the side. Now the area of one of the sides would simply be x times h. So it'd be 4xh. Now this is going to describe the surface area of the box. So you have the area of your base plus the area of the 4 sides. Okay. Now let's see if we can use this formula to eliminate h in our primary equation. Now keep in mind, now some optimization problems you don't need a secondary equation, but this one here we do. You got the 2 different variables, so we're going to have to use this equation to eliminate h in our primary equation. So let's see if we can solve this for h. Now, so we'll solve for h, and let's see what we get. So move the x squared over, so it'll be 108 minus x squared equals 4xh. Divide both sides by 4x. We'll divide this side here by 4x. And this will get 108 minus x squared divided by 4x equals h. All right. Now, solving this for h, now we're going to use substitution. Okay, we're going to substitute this x expression from our secondary equation into our primary equation here. All right, so as we substitute this in, okay, our volume formula becomes, okay, x squared times 108. So 108 minus x squared, okay, divided by 4x. Right, and that eliminates our h variable now. Now I want to remove our my problem here to give me a little bit of extra room to work here. Like I said, we're looking for maximum volume here, so this becomes my volume equation now. Now this is what we're going to take the derivative of, but first let's see if we can simplify it a little bit. Now as you multiply x squared times this fraction, one of these x's here is going to reduce with this x on the bottom. And then multiplying the remaining x inside your parentheses will give us v equals 108x minus x to the 3rd power divided by 4. And then this becomes, now 108 divided by 4 gives you 27, so it'll be 27x minus 1/4 x to the 3rd power. It's a 3, so x to the 3rd power. So this is our volume equation now. Okay, so much easier to take the derivative of now that we've eliminated the h variable, all right? So we only have the one variable there to worry about. Now, one more thing we need to do before we go any further, before we take the derivative and stuff. First thing we need to decide, what about our domain? Okay, when we start solving this for x, what values can x be? So let's take a look at what our domain can be. So our domain, now, so what about our domain in this particular case? We've written our equation, 27x minus 1/4 x to the 3rd power. So what would be a feasible domain? Let's see. Now, first of all, x can't be negative, right? So that wouldn't make any sense. So x can't be negative. Okay, also, now let's see, just how big can x get? Now remember, we have a surface area of 108 square inches, or 108, so 108 square inches. So we have a surface area of 108. So just how big can x be? Okay, well, if h were 1, so if h were 1, the surface area would be 108 equals x squared. Right? So if h were 1, this would be the surface area for x. So the square root of 108 would equal x. So x, now the square root of 108 is about, let's see, a little bit over 10. It's about 10.4. Right, so x really can't be bigger than 10.4. Right, so when you think about it, so if the height were 0, x can't be bigger than 10.4. Okay, also x has to be x has to be greater than or equal to 0. So as we describe our domain, this will be 0 less than or equal to x, less than or equal to 10.4. So anything outside that range, from 0 to 10.4, won't work. Okay, so it won't work. So this will describe our domain. So once we've written our equation here, you always want to think about your domain first. All right, just how big can x be here? Okay, now let's see, we've got our equation written, we've described our domain. Let's see if we can take the derivative now of our volume formula that we just wrote. So let's take our derivative. And let's see, so it'll be dv over dx will be equal to, now the derivative of 27x is 27. The derivative of negative 1/4 x to the third will be negative 3/4 x squared. So this is our derivative. Okay, now we're going to use the first derivative test to see what our maximum value of x would be. Now, using the first derivative test, now first of all we need to get our critical values. You're looking at our derivative here is a little polynomial, right? So there are no values where it doesn't exist. So basically we just need to find the zeros of our volume of our derivative now. So it'll be 27 minus 3/4 x squared. Now we got to solve this for x. Now, so we'll see how many critical numbers we have. Now, solving this for x will give us negative 27 equals negative 3/4 x to the second. So move that 27 over. Now change the signs on both of these, right? So we'll make both of them positive. Now to get rid of that 3/4, I'm going to multiply 4/3 to both sides. So I'm going to multiply by my reciprocal. This will multiply 4/3 to the left-hand side too. That'll reduce to 1, this will reduce to 9. That gives me 4 times 9, which is 36, equals x squared. All right, now taking the square root of both sides, plus or minus 6 equals x. All right. Now, first thing you notice right away, we got two critical numbers, positive 6 and negative 6. Negative 6 is outside the domain, right? So we can't use the negative 6. So I'm going to erase this. So our only critical number would be x equals 6. So x equals 6 would be our only critical number. So let's see, we got our critical number. So let's check this with the first derivative test. I'm going to do me a little, put this on the number line. Put the 6 here. To make sure that in fact that this is in fact a maximum value, all right? So we're going to put v prime here, v here. We'll pick out a test value on each side, so we'll try, so it has to be between 0 and 10, so we'll try 1, and then we'll try 7. All right, so substituting 1 and 7 into our derivative, and let's see what we get here. All right, so okay, let's do the 1 first. So substituting 1 into our derivative gives us 27. So v sub 1 would be, or v prime at 1 would be 27 minus, so 27 minus 3/4 times 1 squared. Now, remember what we said about the first derivative test, the actual number doesn't matter. Okay, what really matters is that this will be 27 minus 3/4, that's going to be a positive number. Right, so if you look at what's happening here with our derivative, right, it's going to be positive. Right, so this is going to be positive here and increasing. Right, so now let's do the derivative at 7. So it'll be 27 minus 3/4 times 7 squared. And let's see, now I did this earlier, gives us, so let's see, we get a positive value. So this is going to be, actually you get a negative value, so this will be negative. Right, so this will be negative and decreasing. Right, so it's increasing to the left, decreasing to the right. So it's increasing here up to 6 and then decreasing. So we're looking at a maximum value at x equals 6. Now the problem asks, now let's see, now we got our maximum value, the x value of our maximum value. Now the problem said to find the dimensions. Right? So we found x. So x has to be 6. So what does the height have to be? So we need to figure out the height. Now to get the height, you got to come back over here to the secondary equation now. So we're going to use the secondary equation to get the height. So x is 6, so this should be 108 minus 6 squared divided by 4 times 6. Okay, this will give us our height. In this case, our height will be 3. Right, so our height will be 3. So the dimensions now, this will be in inches, I believe, right? So it'll be 6 inches by 3 inches. So it'll be 6 inches by 6 inches by 3 inches. Right, right, so 6 inches by 6 inches by 3 inches. Okay, that's going to be the dimensions of our box, right? So 6 by 6 by 3. Okay, let's take a look at problem number 2. So this is actually a pretty good problem to start off with. Just a couple things I want to remind you about now as you're doing these optimization problems. Once you get your volume equation written, or you get your primary equation written, okay, you want to kind of consider the domain. So remember the domain, try to look at the domain, just how big can x be or your variable be, all right? So sometimes I forget to do that myself when I'm teaching, but you always have to think about, just how big does that have to be. So when you get these, when you're solving for x here and you get values that are outside the domain, you don't have to worry about those critical values. All right, so a pretty good problem. Now this one here this problem has a secondary equation. So typically the secondary equation is called your constraint equation, all right? So in our problem here, it can't be bigger than 108. That's our surface area. So you have to describe the surface area of your shape here. Okay, let's try our second problem. So let me get this one erased real quick. Let's try problem number 2. All right. And the problem number 2, I believe, is another volume problem. So let's see. Let's take a look at it. Let me erase this. There we go. And problem number 2. Okay, let's set it up. And once again, you want to go ahead and copy the problem down. If you're working this along with me, you want to go ahead and copy the problem. Now, let's take a look at this problem here. Now, it says make an open top box again. So once again, the top is open by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin. Okay, by bending up the sides. How large should the squares be, and what is the resulting volume? Right. Now, as you look at these examples, these examples are in our textbooks. I'm just kind of working through them and explaining them a little bit. Okay, we use the Larson text, so you can see these are somewhere in our textbook. Most of these are. I think this one is. So we're going to make an open top box, cutting congruent squares from the side, and then bending up the sides to make a box out of it, all right? So to start us off, let's always start off with a diagram. So let's see what we got here. So you got a piece of tin, 20 by 25 inches. So problem number 2, so a piece of tin. Okay, let's see, 20 by 25 inches. Okay, now it says we're going to cut congruent squares out of each corner. All right, so like this, so congruent squares out of each corner. Now the problem says, how large should the squares be? So we're going to try to get the size of the squares. So we're going to let these squares be the congruent squares, x and x. All right, so we're going to get, so basically that's going to be our variable here. Now, so we're going to cut these corners out, and then we're going to bend up the sides to make an open top box. So the box will look, sort of like this. So if I can sketch it here, sort of like so. Okay, there we go. Right. Now you notice when you bend up the sides. I know this entire side right here is 25 inches. So when you take the corners out and bend up the sides, from here to here should be this length from here to here. Right. Now, this whole side is 25 inches. So when you take the squares out, this will be 25 minus 2x. You've got an x here and an x here. The whole side is 25, so it'll be 25 minus the squares. The side of the squares are on each side. And that means that this side right here, inside from here to here, should be 20 minus 2x. So this side right here will be 25 minus 2x. Okay, the other side here will be 20 minus 2x. And when you bend that up, okay, that's going to be our height. Right? Now, once again, I said we're looking for the, we're looking, it says, how large should the squares be, and what is the resulting maximum volume? So we're looking for the maximum volume here again. So maximum volume. Okay, now what we have here, we've got, once again, another rectangular solid, length times the width times the height. And that's our volume being length, width times the height. So in this case, V equals 25 minus 2x, okay, times 20 minus 2x. times the height. So length times the width times the height. So you want to describe the length, width, and height of the box that we just made. So this is describing them in terms of x. And remember now, x is going to be the length, the sides of the squares that we cut out of the original piece of tin. So this is how we're describing our box in terms of our side. Okay. Now, one thing I notice about our volume formula here. Okay, this volume formula is all in terms of x. So v and x. So we don't have two different variables here to worry about. Okay, also we don't have a secondary equation here. So we only have a primary equation only. So this is the only equation we have to worry about. But we do have to simplify this a little bit. So I don't want to use the product rule here and stuff to try to take the derivative. So we're going to have to take the derivative of our volume formula. But first, let's multiply this stuff together and let's see what we get. So let's multiply. First, let's use our full method. Multiply the two binomials together. So our volume will be, now 25 times 20 would be 500. Minus 50x minus 40x. Negative 2x and negative 2x is plus 4x squared times the height, which is x. Okay, combining our two x terms here will give us a v equals 500 minus 90x plus 4x squared. 4x squared times x. So plus 4x squared times x, all right? And now let's multiply x inside our parentheses now. So once you get the two binomials multiplied, okay, let's use our distributive property. Okay, let's multiply x inside, so v should be equal to, now x times 4x squared gives us 4x cubed. X times negative 90x will give us a negative 90x squared. And x times 500 would be plus 500x. Now, when I write my formula here, I'm going to write it in descending order. So I'm going to put the 4x cubed first, just to be a little bit easier to work with, I think. Now, this is our volume formula. So this is our primary equation. And it's only in terms of v and x. So like I said, we don't need a secondary equation here. Now, I'm going to take the problem down. So to give me a little bit of room to work here, so let me remove problem number 2. All right. Now, next thing we need to do, we need to take a look at the domain. And like I said, once you write your primary equation, you get it simplified now. Before you take the derivative, think about the domain of your function, right? So if you don't, you're going to be trying critical numbers that you don't need to try and won't work, right? So let's take a look at the domain. Okay. How big can x be? So just how big can x be? Now, first of all, x can't be negative. So x can't be negative. So x is non-negative. So x is non-negative. That would be with 2 n's. So non-negative. So x has to be non-negative. Okay, so it has to be positive. So just how big can it be? So technically, I guess it could be 0. Right? So you could kind of make an argument that if x is 0, you're not actually cutting a square out. But so technically, I guess x could be 0. Now, just how big can x be? Now, notice, the original piece of tin was 20 inches by 25 inches. So just how big a square could we cut out? We couldn't cut a square out of each corner that's like 100 inches because the original piece of tin is only 20 by 25, right? So just how big can that piece of that square be that we cut out of each of the corners here? Could we cut a piece of, so think about it now, could we cut a piece of, a square out of each corner that would be 20 inches long? Well, if you cut two 20-inch piece squares out of this side, that whole side is only 20 inches. So you couldn't cut two squares that are 20 inches. That'd be 40 inches there together. So actually the two squares could meet you right here. So actually, you could actually cut two squares that would be up to 10 inches. So you can't go bigger than 10 because the smallest side right here is 20. Right? So you can't cut two squares that are anything bigger than 10. So x has to be, so because the shortest side here is 20, okay, we'll say that this has to be 0 less than or equal to x, which would have to be less than or equal to 10. So our domain has to be between 0 and 10. Right? So between 0 and 10. Anything bigger than 10 will not work here. Okay. Now, I believe we've described our domain. Right? I think we are ready. So let me write this up here. So the domain is 0 less than or equal to x, less than or equal to 10. So anything bigger than 10 is not going to work. Right. Now, let's take our derivative, and then we'll be ready to use our first derivative test. So the derivative here, so dv over dx will be equal to, this will be 12x squared minus 180x plus 500. Once again, a little polynomial. Now remember, now you're looking for your critical numbers now. So critical numbers are where the derivative is equal to 0 and where the derivative doesn't exist. Now polynomial exists everywhere. So all we're looking at here, all we have to consider is where the derivative is equal to 0. So let's set this equal to 0. It would be 12x squared minus 180x plus 500. Okay, now a little quadratic equation, right? Now let's see, just looking at this, how are we going to solve this equation? Well, a lot of times you can solve these by factoring them. I see that 500 there, these are kind of some big numbers to try to factor. So I'll tell you what I want to do here. Erase this. Let's see if we can use the quadratic formula here. So that would probably be the fastest way. Maybe I'll solve it by factoring, but that would take maybe a pretty while. So remember the quadratic formula, A would be 12, B is to be negative 80, and C is going to be 500. So let's use our quadratic formula, and let's see if we can solve this one for x like that. So x will be equal to negative b. Now b is already negative 100, so this will be positive 180. Or b is negative 180 already. So this will be a positive 180 plus or minus the square root of negative 180 squared minus 4 times a. Now a is 12 times c, which is 500. All that divided by 2 times a, and a is 12. So 2 times 12. So we'll use our quadratic formula, and this will make this a little bit easier to solve. So now let's see what we get. Now I'm going to do excuse me, I'm going to use the positive value first. I'm going to do 180 plus the square root of your negative 180 squared minus 4 times 12 times 500. And all that divided by 2 times 12. And let's see, what do we get here? And let's see, I've already done it in my notes here. We get x equals, for the positive, we get x equals 11.319. One value, and the other value we do the negative. So you do 180 minus your radical divided by 2 times 12 gives us x equals 3.681. So 3.681. Right. So you got two critical numbers. You got x equals 11.319, x equals 3.681. Okay. Now right away you notice, or you should recognize right away, that 11.319, this is outside our domain. Right, so we're not going to use the 11, all right? So that's too big. So that square cannot be 11.319. Now 3.618, yes, it can possibly be 3.618. So I'll tell you what we're going to have to do here. Now we got our one critical number. So let me write this down up here. So x equals 3.681. All right, so 3.681. Check my notes and make sure that's correct. Okay, I think we're good to go. All right. And once we got our critical number, let's do let's put this on a number line graph. Let's see if make sure this is in fact a maximum. We're maximizing our volume. So it's on a wiggle graph, if you will. All right, and this will be v prime and v. We'll put the 3.681 here. And let's pick us out a test value on each side. Now it has to be between 0 and 10, so we'll try 1 and 4. All right, so 1 and 4. All right, so the derivative at 1. So let's see the derivative at 1. And let's see, our derivative is 12x squared minus, so 1 squared minus 180 times 1 plus 500. Okay. Now, I've already done this. This comes out to be a positive 332. So a positive 332. Now remember, the number itself really doesn't matter in the first derivative test. All that matters is that it's positive, right? So the derivative is positive. Okay, that means that v is increasing, all right? And then trying positive 4, so v prime at 4. So substituting 4 in for x, and I've already done this as negative 28. So negative 28. Okay, this will be negative. So the derivative is negative, that means it's going to be decreasing. Okay, so by the first derivative test now, our graph is going to be increasing up to 3.681, and then it should be decreasing. So you're looking at a maximum value for our critical point. So we've got a maximum value there, and Let's see, now what else do we have to get? So also it said to actually find the volume, didn't it? So I believe our problem said to, what would the resulting volume be? Now we got the x value, so the maximum volume would be a square that's 3.681 inches, all right? So that would be our critical number, that would be the length of our square. So to get the maximum volume, we have to use our volume formula that we had written here, right? So let's take this, let's substitute the 3.681 into our volume formula, and that should give us our maximum volume. So the volume at 3.681, okay, which would be 4 times 3.681 cubed minus 90 times 3.681 squared plus 500 times 3.681. So you got to take the 3.681, substitute it into your volume formula, okay, which is, and I've already got this done, this is 820 point. So 0.528. So 528. And I believe this is in inches, so this will be in inches cubed. Now, so the maximum volume should be 820.528 inches cubed. All right, so this is a nice example of a volume, an optimization problem in which you don't need a secondary formula here, or a secondary equation. You only need the primary equation. So the only constraints here was the length of our square that we could cut out of each side. Okay, so a pretty good little problem. Let's try problem number 3. Let's try another one. All right, so we've done 2 volume problems. Let's try an area problem or 2. So we'll do an area problem. So let me erase this. All right, so let's try some area problem. Okay, now our next problem, this will be problem number 3. All right, so we're going to design a can. Here we go. All right. That says, now here it says design a 1,000 milliliter can. An oil can can be shaped like a cylinder. Right, so a cylinder is like a can, like a pop can. What dimensions will use the least material? So what dimensions will use the least material? Okay, so this time, let's see, start off with a diagram, all right? So start off with a diagram, talk about a can. Yes, here's our can. Okay, that'll be the radius, that's the height of the can. All right, now let's see, it says, what dimensions will use the least material? All right, now let's see, it says design a 1,000 milliliter oil can. Now 1,000 milliliters, that's our volume, right? But the actual problem says what dimensions will use the least material. Now the material would be the sides and the top and the bottom of the can. So you're talking about basically the surface area. This problem here we're looking at maximum, or it's actually minimum surface area. So we're talking about the least material, right? So this will be the minimum surface area. So minimum surface area. Okay, so the minimum surface area. So to get started, we're going to have to write our surface area formula. Now, I don't know if you remember, some of you from geometry, you may remember the surface area of a right circular cylinder like we have here. Now, if you can't remember it, just remember as you describe your surface area, you've got the 2 ends. Now, if you take the can and flatten it out, you have the lateral area of your can. So you got the top and the bottom. Okay, this is your radius. Okay, this is your radius. Now, the bottom of the can here would be the circumference of the circular area. So the circumference would be 2 pi times the radius. Okay, this would be the height. So as we describe our surface area, so the surface area would be, you got 2 circles. Now, the area of the circle would be pi r squared, pi times the radius squared. So the surface area would be 2 pi times the radius squared, plus our lateral area. Now, this is when you flatten the can out, you end up with a rectangular area now. The bottom of the rectangular area is 2 pi r. That would be the circumference of your circular area. So it would be 2 pi times the radius times the height. That's our surface area formula. Now I'm just going to call it A. Right? So our surface area formula A equals 2 pi times the radius squared plus 2 pi times the radius times the height. Now I'm sure hopefully most of you remember that from your geometry classes. This is our surface area formula to find the surface area of a right circular cylinder. Right? Now also you notice that the surface area formula is written in terms of R and H. So really we need to see if we can remove one of these variables. Two variables makes the problem much more difficult to work with. So let's see if we can eliminate this. Luckily, in this problem, they give us a constraint. And the constraint is the volume of the can. The volume has to be 1,000 milliliters. So what's going to be the minimum amount of material that we can use? So remember, if you're an engineer and they ask you to design a can like this, this would be the type of problem that you may have to work. So a 1,000 milliliter oil can, and the minimum amount of material, the more material you use, right, the higher the cost and the smaller the profit would be. If you actually have to make these commercially, it's not a can, right? Okay, so the 1,000 milliliters, that's going to be our secondary equation. So let me erase this. So that's our surface area. So our surface area, this is going to be our primary equation. Now, in just a moment, okay, we're going to take the derivative of the surface area, right? So we're doing minimum surface area, right? So now, hopefully you remember now the volume formula for a cylinder. So 1,000 milliliters are volume. So the volume is pi times the radius squared times the height. In this case, 1,000 equals pi r squared times the height. Okay, now we're going to use this formula now. This is our secondary equation, right? So this is our secondary equation. So we're going to use our secondary equation to eliminate h out of our primary equation. So we're going to use it. So if you have two different variables like this, if you have a constraint, okay, this is our secondary equation, or sometimes called the constraint equation, right? So let's take our volume formula now. Let's solve this for h. And then we'll substitute it in over here in our surface area formula. Now, solving this for h, we're going to divide the right-hand side by pi r squared. Now, these will cancel. Let's divide this side here by pi r squared. So we have 1,000 divided by pi times the radius squared is equal to the height. Okay. Now, solving this for h, now let's plug it, substitute it into our primary equation over here, our surface area formula. Okay, we have a equals 2 pi times the radius squared plus 2 pi r times, now let's substitute 1,000 over pi r squared. So we'll take this, our volume from our volume formula, right? We're going to replace the h now with this r expression that equals h. Okay. Now, see, we got our surface area formula now written just in terms of r. But let's see if we can simplify this a little bit, all right? So so we can kind of clean it up a little bit. So to start off, let's see if we can multiply. So I'm going to erase this here. Okay, our surface area here is going to be 2 pi times the radius squared plus. Now, let's multiply 2 pi r times this fraction. Now, right away you notice that the pi's are going to cancel on the bottom of that fraction. So you multiply that. Okay, those are going to cancel out. Also, this radius is going to cancel out with one of those radii on the bottom here. You got two r's, and one of those radius is going to cancel out. And that gives us 2 times 1,000, which is 2,000, divided by r. Okay. Now, this is our area formula. This is the one we're going to have to take the derivative of. So, to get started, let's see if we can describe the domain. So, what restrictions on the domain do we have? So, the domain. Right, now, the domain, our surface area formula now is written in terms of r. Now, just how, what can r not be? Now, first of all, once again, r can't be negative. Okay, also, you look at our surface area formula here, r is on the bottom of that fraction, so technically r cannot be equal to 0 either. So remember, if r is equal to 0, 2,000 divided by 0 is not defined, so r can't be equal to 0. But actually, other than that, there's really no constraints on the radius. The radius can be as big as you want. It can't be negative, and it can't be 0. We'll say the radius has to be greater than 0. So that's really the only, that's going to be our domain. So anything bigger than, it just has to be bigger than 0. That's it. All right. Now let's see if we can take the derivative of our surface area formula, and I'm going to take the problem down. So hopefully you have it written down by now. I'm going to take this off to give me a little bit more room. Okay. Now to take the derivative down, we've got 2,000 over r. So first thing I'm going to do, I'm going to pull that 2,000 off. Let's rewrite this. A equals 2 pi times the radius squared plus 2,000 times r to the negative 1 power. So let's rewrite it. It's that little fraction. You don't want to have to use the quotient rule to take the derivative of a little fraction like this. Now we're ready to take the derivative. right? So we have dA over dx is equal to, so the derivative of a with respect to, actually be over dr, I guess, so we use r. So dA over dr will be equal to. Now, taking the derivative of 2 pi r squared gives us 4 pi r. And then taking the derivative, here you go, of 2,000 r to the negative 1 will give us a minus 2,000 r to the negative 2 power. Now, let me rewrite this. This would be dA over dr equals 4 pi r. So 4 pi times the radius minus 2,000 over r squared. Okay. So we've got our derivative. All right. Now let's see. First of all, what would be our critical numbers? All right. So what would be our critical numbers? So r prime is equal to 0. R prime does not exist. All right. Now, first of all, r can't be equal to 0. So r squared cannot be equal to 0. So r equals 0. That would be one critical number. But luckily for us, 0 is not in the domain. All right. So we don't have to worry about this. So let's find the zeros of our derivative then. So substituting 0 in. So setting this equal to 0, that gives us 4 pi r minus 2,000 divided by r squared. Okay, subtract 4 pi r on both sides, so it'll be negative 4 pi r here. On the left-hand side equals negative 2,000 over r squared on the right-hand side. Let's change the signs on both sides. Now, I need to get r squared out of the bottom of that fraction, so let's multiply r squared on this side. It's going to cancel out. And let's multiply r squared on the left-hand side. So multiply r squared to both sides, and I'm going to have to bring this over here if I want to run out of room. Now, you get r squared times r gives you r to the third power now. So we end up with 4 pi r cubed equals 2,000. So hopefully you can still see this. I'm working over on the edge of my board over here. So equals 2,000. Divide both sides now by 4 pi. So we're going to try to solve for r. So divide this side by 4 pi. 4 pi's will cancel. It gives me r cubed is equal to, now 2,000 over 4 pi. Let's see, the 4 will cancel out to 1. This will reduce to 500. So we have 500 over pi. So what it is, r cubed equals 500 over pi. Now, to get rid of that cube exponent, you're going to take the cube root of both sides. So we'll do the cube root of this side here. So r is equal to the cube root of 500 divided by pi. Okay. Now, if you're looking for the exact radius, this is it here. So the cube root of 500 over pi. Now, so this would be the exact radius. Now, we're going to have to, if your boss were to ask you, what's the maximum radius, you don't want to give him the cube root of 500 over pi. He's going to ask you, what's the real radius? So you're going to give this, let's see if we can put this up on your calculator, see if you can get a decimal on it. And when I did that, I got 5.419. So the radius would be approximately 5.419. Right, so it's approximate 5.419. Okay, so that'll be our radius. Right, that's our critical number. Now let's put this on a wiggle graph now. And let's see, I'm going to have to erase. I want to erase some of this. Let's see, so we've got dA, erase this right here. So put this on our wiggle graph, all right? So I'm running out of room here fast. This will be 5.419. This will be A prime and A. So our surface area. And now when I check this using the first derivative test, I use 1 and 6. So I use positive 1 and positive 6. So substituting these in. Now to save a little bit of time here, substituting these into your derivative here, right, gives us, negative and then positive. Now, so it's going to be decreasing to the left, increasing to the right. So decreasing and then increasing makes that a minimum. So that is our minimum value, all right? Now let's see, what do we have to find now? Let's double check here. So what are the dimensions? So we're looking for the dimensions that would use the least amount of material, right? So the dimensions. Now let's see, we've got the we've got the radius. So the radius will be 5.419. Okay, we still need to get our height. So let's get the height of our can too. So to get the height. So to get the height of the can. Let's take the radius and plug it in over here. So it'll be 1,000 divided by pi times 5.419. Now, if you're taking an AP calculus class, now this number right here you don't want to round off. So if you've got this in your calculator here, it'd be 5.419260. So 701. So 701 squared. Because remember now, if you're taking AP calculus now on the AP calculus exam, you're going to round your final answer off to 3 decimal places. So if you round this answer off too soon, it could cause you to round your answer off incorrectly. So, if you're taking AP calculus, then you don't want to round your critical number off too soon. You want to go ahead and put the entire number in, at least so that's so many digits. So for our height here, I got about 10.839 centimeters. So about 10.839 centimeters. All right. So our dimensions. We said the radius. So R equals 5.419. This will be centimeters, and the height is equal to 10.839 centimeters. So we got our radius and we got our height. So this is a pretty good example of a minimum surface area. Right? So this would be the type of problem engineers work with these types of problems all the time because they want to minimize the amount of material they use. All right. So let's try one more example. Let's try one more. So let me erase this one. Okay, we'll do another area problem. So let me erase this here. Okay, so we'll do one more area problem. Here we go. Okay, this will be problem number 4. And let's go ahead and bring it up. Okay, this is a page. A piece of paper, a page of page, right? Now it says a rectangular page contains 24 square inches of print, right? So the margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. Okay, what dimensions will use the least amount of paper? So what dimensions will use the least amount of paper? So you're talking about a piece of paper basically, right? So something like this. Right? So we're talking about a sheet of paper. And you've got some print, so you got a margin at the top. So at the top and the bottom, the margins are 1.5 inches. So 1.5 inches at the top and the bottom. On the left and the right, the margin is going to be 1 inch. So 1 inch this way here. And in the middle, you've got the print. So in the middle, we have the amount of print. So what dimensions will use the least amount of paper? Right. So let's see, we're going to describe the length and the width of the sheet of paper. So to get us started, it really doesn't matter what variable you use for the length and the width. I'm going to let this be y and this side be x. All right, so y and x. Okay, now what I need to do, I need to describe the bottom side of my piece of paper. All right, now we said the dimensions were, let's see, it was on the top and the bottom, it was what, 1.5. 1.5 here, 1.5, and to the left and the right was 1 and 1. So the left and the right was 1 and 1. So if you're going to describe this bottom side, this will be the length from here to here. So it'll be y plus 1 again, would be y plus 2. So the bottom side of our piece of paper, we're going to describe it in terms of y, would be y plus 2. Now, let's describe the length this way. So this is in terms of x. Right, so this is 1.5 here, 1.5 there. So the right-hand side of our paper, what would be the length, would be x plus 1.5 plus 1.5 would be x plus 3. Okay. Now, so we're looking at this. So what dimensions will use the least amount of paper here? So once again, we're talking about minimum area. Right, so minimum area. Now, the area of a piece of paper, this is just a rectangle, so the area, remember, is length times width. All right, so just the length times the width. So in this case, it will be, see, A equals, this will be x plus 3 times y plus 2. All right. Now, as you describe our area, now you look at our area, you got x plus 3 and y plus 2. You got the two different variables there, x and y. We need to see if we can eliminate those. Now, If you notice now in our problem here, so the rectangular page contains 24 square inches of print. Okay, that would be the center area here, wouldn't it? So 24 square inches of print. Now the area of the center region here, just the print, would be 24 equals x times y. So our constraint equation, if you will, or our secondary equation would be 24 equals x times y. So that would be the area of the print in the middle of the page. All right, now we're going to use this equation to eliminate, in this case we'll probably eliminate y. I like just to keep it in terms of x, but you could actually eliminate either variable that you wanted to there. Now to solve this for y, so let's solve for y here. So solve for y, we're going to divide this side by x, divide this side here by x. We have 24 over x is equal to y. Okay, now once you get it solved for y, let's substitute it into our other equation over here. So let me erase this. And we end up with a equals x plus 3 times, instead of y, we'll put 24, so 24 over x plus 2. Okay, so we have this expression now, or this function to describe the minimum area, or the area of the length and the width, or the size of our rectangular page, if you will. All right. Now let's see if we can simplify this a little bit. So we're going to have to take the derivative now. Hopefully you got the problem copied down, because I'm going to have to take it down to give myself a little bit more room to work again. So eliminate this. Right. Now let's see if we can simplify this. Now to multiply these, so we're just going to use FOIL. You got to use the FOIL method, right, to multiply these. So our area becomes. Let's see now, x times 24 over x. Now remember, as you multiply x times 24 over x, and x's cancels out, it gives you just 24. So multiplying the first terms is just 24. X times 2 gives you 2x. 3 times 24 over x, when you multiply 3 times 24 over x, it gives us 72, so it'd be 72 over x. So it'd be plus 72 over x. And then multiply the last terms. 3 times 2 gives us 6. So when you get that multiplied, okay, this is what your product will look like. So you're going to do first, outer, inner, last. You're just multiplying the two binomials. It's kind of odd multiplying with this fraction there. A lot of students aren't used to that, but this would be our product. Now let's go ahead and add the 24 and the 6 together. So a equals, let's see, a equals 2x plus, now 72 over x, I'm going to write that as 72x to the negative 1. And 24 plus 6 gives you 30. So this will be our area. This will be our area formula in terms of x now. Okay. Now, this is how we describe our domain. The domain here would be, so to describe the domain of the function now. So once you write your equation now, let's see just how big x can be. And basically, I guess, just looking at the domain, x can be 24, so x will pretty much have to be positive. So x can't be, x couldn't be negative here, so x would pretty much have to be greater than 0. So x greater than 0. So let's see if we can take our derivative, and let's see what we get for our area now, right? For x. So taking the derivative of the left-hand side here, so it'll be dA over dx is equal to, now the derivative of 2x is 2. The derivative of 72x to the negative 1 would be negative 72. Negative 72x to the negative 2, and the derivative of 30 is 0. So we find your derivative. Now, when we write this, this will be dA over dx equal to 2 minus 72 over x squared. So I'm going to write it like this. All right. And let's see now, as you consider our critical numbers now, so our critical numbers, remember, a prime equals 0, or a prime does not exist. Right? Doesn't exist when x squared is equal to 0. That's x equals 0. Now, once again, 0 is not in the domain, so we don't have to worry about the 0 here. So let's get the zeros of our derivative though. So second derivative equals 0. So 0 equals 2 minus 72 over x squared. And let's solve this for x. Let's see what we get. Let's see, I'm going to come over here to do that. So let me erase this. All right, so the 0 equals, now let's bring the 2 to the left. So we end up with negative 2 equals, negative 72 over x squared. Change the signs on both sides, right? And it gives us 2 equals. Now change the signs on both sides, and I'll tell you what, so we'll save us some time. Let's multiply x squared on both sides. Remember, we got to get x squared out on the bottom of that fraction. And that gives us 2x squared equals 72. On the left-hand side of our equal sign, we end up with 2x squared, that'll be equal to 72. That's what's left. Divide both sides by 2. X squared is equal to 36. X will be equal to, so x will be equal to plus or minus 6. And remember, x can't be negative, so we only need a positive 6. X is equal to positive 6. Okay, so we got our one critical number ready that we can use. The 0 we said we couldn't use. So x has to be equal to 6. Now let's see, let's try our critical numbers now. I'm going to run out of room here real quick. So let's try our, this little wheel graph. So we'll put the 6 here. So this will be a prime and a. And I'm going to try, now the two numbers that I'm going to try, let's try 1 and 7. Right? So we'll try 1 and 7. Right? Now let's see, substituting 1 into our derivative. Right? So here's our derivative. So this would be a prime at 1 would be 2 minus 72 over 1 squared. That'd be 2 minus 72, which is negative. All right, so the negative, so this is decreasing on the left. Okay, substituting 7 in for x, you end up with 2 minus 72 over 7 squared, which is positive. All right, so this is positive, so it's going to be increasing. So if you look at what's happening, so it's decreasing, then increasing again. So you're looking at a minimum value. So the first derivative changes from negative to positive, so you're looking at a minimum value, right? So remember now, in the first derivative, the first derivative actually has to change signs at your critical number before you have a minimum or maximum value. If there's no sign change, then you don't have a minimum or maximum. Okay, so we're going to have a minimum at x equals 6. And let's see, what else did we have to find here? It says, what should be the dimensions of the page? So we actually have to find the dimensions of the page. Now we've got x equals 6. Now you've got to be careful with this type of problem that you don't stop too soon. Right, so they didn't just ask us to solve for x. Right, so x is going to be the inside print length, the length of the inside print, the print area, I guess. So to get the actual side would be, let's take the 6 substituted in here, would be 6 plus 3 or 9. So one side should be 9. And let's see, so one side should be 9. And what would the other side be? So let's see, one side should be 9. And let's see, let's get y also. To get y, I'm going to go back to our, so to get your other variable now, you got to go back to your secondary equation. Now this would be, so we're going to find y here, so it'll be 24, x is 6, so it'll be 24 over 6, which is y, so y would be equal to 4. Right, so y is 4. Now that's not my answer yet, right? That's simply the y value in my side here, so it'll be 4 plus 2, so this side would be 6. So we're looking for our dimensions. Right, so the dimensions would be, let's see, this is in inches, I believe, so it'll be 9 inches by 6 inches, so 9 by 6. So once you get x and y, make sure you substitute in here. We're looking for the actual length of your page, so it'll be 9 inches by 6 inches. Okay, so this is a pretty good area problem. Once again, you had to use your secondary equation here to eliminate y in your primary equation. So sometimes, a lot of times, they'll give you a constraint like we had here. It gives a constraint of 24 inches for the inside area of the print. So that put a constraint on it, and from there we can set up a secondary equation, and then we can eliminate one of our variables. Okay, so hopefully you found these 4 examples helpful. One thing about optimization problems, they're kind of all different. So depending upon the situation, there's not really one way to do every problem. So